So good afternoon, everybody, and thanks for inviting me to present our work. I'm going to talk about our fully HTS machine for electrical aircraft propulsion applications. So I'm from the Applied Superconductivity Laboratory at the University of Strathclyde in the UK. Okay, so I'll give you a brief background of why we're interested in this work. So as a hot topic now, so hydrogen can enable zero emission aviation as a zero emission fuel for future aircraft. So there are currently two types of popular hydrogen powered aircraft. First one is to use liquid hydrogen combined with a fuel cell to provide the electricity for electrical powertrain and including electrical motor to drive the fan to provide the propulsion thrust. So we have seen example project, for example, in the NASA funded the US Cheetah project and to looking at liquid hydrogen powered powertrain for the aircraft. And in the UK, we have this GKN leading a program called H2 Gear, so looking at a liquid hydrogen propulsion system. And also we can use liquid hydrogen to power gas turbine and then to drive a generator to generate electricity, alternatively for a propulsion network. But in both these system architectures, we will know that there's a cryogen, which is liquid hydrogen on board, and both these electrical propulsion units showing here are needed with high power density requirement for aviation purpose. So for this system topology, we have seen examples from Siemens and Rolls-Royce e-aircraft study. So as I said, so for aircraft propulsion applications, these electrical motors need to be with high power density and also high efficiency. So a very popular concept now is to using liquid hydrogen to cool down the conductors and the drives to increase their power density. And then by using superconductors, we can increase both the power density and efficiency of the whole powertrain and the drives. So we have seen example project, for example, the Airbus ASCEND project to explore liquid hydrogen and superconductivity combined function as a cryogenic powertrain for aircraft propulsion. And also, if you look at this figure produced by NASA, so in terms of the power density, you see the red one is the requirement for conventional gas turbine cores currently used in the aviation sector. And this brown one shows you where the conventional motor or machine's power density is. And then the blue line shows the fully superconducting machines predicted the power density, which goes above the conventional requirement to replace the gas turbine cores. So that's why we are very interested in this fully HTS machine research. So in the Applied Superconductivity Laboratory, so we have set up a 10 kilowatt ultra-flux HTS motor testing platform. So far we have done 77 Kelvin test at 300 RPM. So we have carried out AC loss measurement as well as transient test. So for this presentation, I'll be focusing on 3 points. The first one is AC loss measurement of a fully HTS machine. Second one is the transient test result. And finally, so we have done a theoretical calculation for a fully HTS machine to predict the maximum power density and efficiency offered by the state-of-art 2G HTS material. And I will summarize our findings in this presentation. So the first one is AC loss. So we try to answer this question. So how to measure the losses of superconducting winding in a rotational machine environment? So we set up and developed an actual flux machine. So we have superconducting armature winding here, you see here. So one stator coil and two permanent magnet rotors are showing here in this picture. So these two, a pair of permanent magnet rotor generates a 0.1 0.45 Tesla in the air gap, as shown here measurement data. So we have 2 pole pair, and then the whole system working 77 Kelvin. So in between the air gap, we insert a separate measurement chamber for one of the superconducting armature windings, so we can use the buoy of rate of liquid nitrogen to measure actually how much AC loss is dissipated in one of the windings. Okay, so this picture shows you the actual measurement chamber. So the external one is a larger liquid nitrogen chamber, and the inner one also a separate, smaller liquid nitrogen chamber. So our purpose is actually to measure how much heat can be rejected into the liquid hydrogen as a fuel on board the aircraft. So we use this calculation here. So the methodology is called the calorimetric measurement. So basically, if you put a piece of superconductor inside liquid nitrogen, the total heat will transfer a buoy of the liquid nitrogen into a nitrogen gas. So by using a flow rate to measure the flow rate of nitrogen gas and use this equation, we'll be able to calculate how much is the AC loss generated in the superconducting winding. So this is the full system setup. So you see the long pipe here connected to a flow rate. So we are real-time monitoring the flow rate and then do time integration over a short period of measurement time in order to calculate the total losses generated inside the superconducting coil here while we are rotating the 2 permanent magnet rotors. Okay, so we have done system calibration, so to calibrate the background heat flow and the rotational heat losses and terminal heat losses in order to remove all this heat that which might potentially get into the inner measurement chamber. And then we also put in a heater inside the inner measurement chamber. So we put it fix the power for the heater, measure the flow rate as showing here in the blue one, and then we plot the heat power versus flow rate a constant plot here. So by comparing the ratio of this linear plot to the latent heat of what we call the flow rate constant of liquid hydrogen, so we can know about how much error our system is producing. So currently for this setup, we produce roughly 2.4% of error. So we conclude that there's no significant gas leakage within our measurement chamber, and this system can be used reliably to measure the total AC losses of a fully HTS machine. And then we set up some example coils and then to measure its losses. For example, this one, so we use a superpower insulated conductor. So in total 25 meters. So this figure shows you the self-field critical current and the in-field critical current measured inside the motor. And then we use the setup to run the machine at different speed, and the blue one shows you the speed of the machine, and the red one shows you the flow rate we are monitored. And then by using the equation, we're actually calculating the total losses generated inside the superconducting armature winding. And in contrary, this is the transport loss measured by electrical method. So by doing this measurement, we get to the conclusion. So our motor setup at 300 RPM, 77 Kelvin, the armature efficiency is 99.2%, while at 1,500 RPM, its efficiency is 96%. Okay, so after the AC loss measurement, so we move on to do a transient test. So we are connecting the superconducting machine sitting here to a cryogenic rectifier and operate the machine in a generator condition. So it generates a 3-phase electricity to the rectifier, cooled down by liquid nitrogen, and then feed the DC power into a load bank here. So that's a setup, and this is the 6 diode we used to build the 3-phase rectifier. And then we create a short circuit fault in this this diode 4. So basically, so during the short circuit, when we have the phase B voltage of the HTS machine higher than phase A, we will see a short circuit event happening between the phase B. So the current flow directly between phase B and the phase A the same. So when the phase B voltage higher than phase C, we see current directly flowing phase B to phase C, short circuiting the coils. And then, so that's what we measured during the transient. So this is steady state. So three-phase output from the superconducting motor and then to a DC output of the rectifier. And this is where the short circuit event happens. So we see immediately the DC voltage output dropped, and there's a change in the three-phase AC output of the machine. So we then measure the flow rate during the operation. So this part shows you the normal operation of the machine, and then this is when the coil actually quenches. So for the phase A coil, so the current goes above 80 amps, which is about 25 amps higher than the infused critical current, which means the coil actually quenches during the operation. And then you will also see a dramatic increase in the boil-off rate of nitrogen inside the measurement chamber. So all this large current will be pushed into the copper stabilizer of the HTS coil. And then we also done a simulation in MATLAB to find a consistent agreement between the measurement, which is showing in the red one, and the simulation black one. So for the simulation, we are using an equivalent resistance value for the HTS armature winding. It's a 60 microvolt ohm. So we get to the conclusion that during the fault and quench, so the HTS coil quenches and its resistance value increased by about 30 times. And then we also get the coil out and monitor the critical current again after quench. And then we also observed a damage. So you see here, so outermost turns there's a mechanical damage, but the whole coil there's no burning within the coil. So our conclusion showing here, so the quenched HTS coil acts as a full current limiter itself. So in return, it limiting the fault current level. So we observe no electrical or thermal damage of the coil. But one coil suffered from a few tons of mechanical damage due to lack of impregnation. So we didn't put epoxy around the coil. So we want to freely change the coil winding. But we get to the conclusion that HTS propulsion machine can be fault resilient. So there's a self-protecting function if we use the quench resistance of this tape and choose their copper stabilized layer thickness nicely. But it's vital to provide a reliable insulation and impregnation for its mechanical support, because these windings can suffer from mechanical damage during fault. So that's the lesson we learned from this test. And then finally, so we used the TA formulation we proposed 5 years ago to model the benchmark. We call the baseline fully HTS machine. So this is a 2.67 megawatt machine. So you see HTS racetrack coils in both the rotor and the stator, so air-cooled machine. So we use a concentrated racetrack winding and 8-6 design to maximize winding factor. And then in this simulation, we consider 3 different scenarios, different widths for the HTS width, stator width. For example, so assuming we are using this striated HTS tapes, so each striation can be 1 millimeter, 0.5 millimeter, 0.25 millimeter wide. And then we then calculate the stator efficiency for all the different designs. So we get to the conclusions that if we can reduce the filament size of the HTS winding to below 0.5 millimeter, so we can achieve a very good efficiency for the HTS armature winding here. And then we also calculate we call it upper limit of the machine. in terms of power density, that's the HTS. So we divided by total power of the machine over the weight of the HTS material. So we get to a conclusion that using state-of-art HTS material, so the upper limit power density of this design is 54 kilowatt per kilogram. But there's room for improving, as you'll see. So this is a plot for one of the rotor when it reaches the critical state there for this turn. But there are still a lot of superconducting materials internally which can potentially be used to carry more current. So if we split the rotor coil into different sections and to apply different amount of current into each section. Okay, so get to the conclusion for our we call it proof of concept study. So first question, so by measuring the AC losses, we know how much heat will be rejected into a liquid hydrogen fuel. So so the first conclusion is that so liquid cryogen is not free for any hydrogen aircraft. So we have to make sure the propulsion system efficiency is high enough. So for our demonstrator, we can achieve a 96% of HTS efficiency. And at a lower temperature, we can achieve 95.9% of HTS armature efficiency using the baseline motor design. And what will happen to a superconducting machine in a fault scenario? So we found that HTS windings can be self-protecting because during quench, the resistance value of the winding can automatically be increased by at least 30 times to help limit the fault current. On the other hand, we want to provide impregnation for these windings to prevent mechanical damage. And finally, so based on our baseline design, so the theoretical maximum power density we obtained for the 2.67 megawatt machines is 54 kilowatt per kilogram. Thanks a lot for your attention. So any questions?
In the actual experiments,
yeah.
When you cooling to 25 Kelvin, did you use liquid hydrogen, or did you do any cooling with hydrogen at all?
No, we use helium gas circulation cooling.
Have you considered the risks for using hydrogen when in actual use in the aeroplanes?
Yes, I think for risk issue concerns, we will not have liquid hydrogen or hydrogen gas directly circulating into our propulsion unit. So in our system design, we actually have a heat exchange. So we use a secondary coolant. So the secondary coolant currently we are choosing is the helium gas. So actually we use the helium gas to absorb cooling power from liquid hydrogen tank and then circulate the pre-cooled helium gas into our propulsion unit to help cool down the machine. So that's for the risks, control the risks.
Thank you. There is one last question.
Yeah.
Thank you, Dr. Zhang, for your interesting presentation. And I would like to ask you to provide us a more general comments on which scientific and technical tasks should be still solved in order to have these electric aircrafts in our everyday life, when they will come to the market. Thank you.
So that's something I would say is the next step, a main difficulty facing the broad application of superconducting machines in the aviation sector.
Thank you again, Min, for this nice presentation and answer.